Hi guys, Sajjad Hussain again with a new video. In this video I am going to show you how to calculate the wind load on a 30 by 60 by 15 feet commercial building which is located in Texas, Corpus City as shown over here. I took this example if you refer my previous video. So I took this example from guideline to calculate the wind load as per ASC 702, and this is example number 2. But what I did, now I am using ASC 716 to calculate the wind load as per simplified method on this building. Let me show you the building. Here is the building shown. It consists, the framing is CMU wall on 3 sides. Consider this as a rigid building. Steel framing in front with glass, open web joist, 30 feet span at 5 feet center, etc. Roof metal is 2 feet by 20 feet long. Doors and glass size vary. Glass is debris resistant. So here is the figure. In this direction this is 30 feet, in this direction this is 60 feet, the height is 15 feet. Now I'm using this guide to use the wind load provision of ASC 702 by Kishore C. Mehta and James Delahaye. This example is taken from there, but of course this example is based on ASC 702, but now I'm going to use ASC 716. So I took, as my previous example, I took the latest data from ATS website for Corpus Christi area in Texas. Last time, as I showed you, ASC 705, the wind speed recommended was 125 miles per hour. But for ASC 716, the recommended wind velocity for seismic category 2 structure is 144. And I explained to you that in ASC 705, the wind was treated as service load, and now in ASC 16, rather after ASC 710, the wind is treated as ultimate load. So because of that, load combination is changed, and because of that, the wind velocity is also increased. Other parameters are here. Exposure category is C, occupancy category 2, importance factor I is now 1 for all type. The topographic factor KZT is 1. Ground elevation is again 1. The ground elevation factor KE, which is a newly introduced parameter. The wind velocity is calculated as per equation number 26-10-1. The same old equation, but now they have dropped this factor I, importance factor I, because the importance factor I for all type of building is 1 now. So it should not be used anymore. So they have deleted this or they have dropped this parameter from this equation. Or Kz is of course the velocity pressure exposure coefficient as section 26.10.1. The directional coefficient Kd is 0.85 as per ASC table 26.6-1. The roof is flat, the slope is 0 degree. Now, in my last video, I calculated this, the wind pressure as per chapter 27, but now I am going to use chapter 21, chapter 28, and in chapter 28 there are two parts, part 1 and part 2. I'll show you what is the difference. I'll explain. So here is the workflow. This flow chart shows how to calculate the wind pressure. The wind load as per ASC 716, it starts with chapter 26, and all the parameters and their reference points are given over here. So this is a very nice workflow which gives you a very detailed information for all the steps needed. For example, the basic wind speed V, it can be calculated from section 26.5, or the figures are given from figure 26.5.1 and 26.5.2, etc. But now all this data is available at ATC website, and I took this data from ATC website. Now for your local conditions, you can check the local code, and as per the local code, you should take the wind velocity. But here there is a point. The catch is, if in your area, if the wind velocity is defined before 2010, that means this wind velocity will be giving you a service load. It will not give you an ultimate load. So for ultimate load, generally as per IBC, there is a factor that you can multiply it by 0.29. You can add that rather, or you can multiply by a factor of 1.29 to convert that velocity, that service load velocity, into an ultimate load velocity. So here now I am taking the ultimate load velocity directly from the website. The directionality factor KD is 26.6, exposure 26.7, topographic factor KZT is from 26.8, ground elevation KE is from 26.9, velocity pressure is 26.10, gust factor is 26.11, and enclosure classification is 26.12, and for internal pressure GCPI is from 26.13. Then there are two parts. One is applicable for main wind force resisting system, and the other for component and cladding. So for main wind force resisting system, you can go to chapter 27. Chapter 27 will give you directional procedure for all heights. Chapter 28 will give you envelope procedure for low-rise building. So what I have done before, I calculated the wind load as per chapter 27, and I used this directional procedure for buildings of all height. But now I am going to follow for the same problem chapter 28, and chapter 28 is envelope procedure for low-rise building. So let us go to chapter 28 and let us see what are the provisions given over here. Now in chapter 28 there are two parts. Let me show you part 1 and part 2 both. Chapter 28 says wind loads on buildings, that is main wind force resisting system, and this is envelope procedure. And there are two parts. Part 1 says enclosed and partial enclosed low-rise building. This says, especially the note is there, use part 1 of chapter 28 to determine the wind pressure on the main wind force resisting system of enclosed, partially enclosed or open low-rise building that have a flat, gable or hip roof. These provisions use the envelope procedure by calculating wind procedure from the specific equation applied to each building surface. For building shapes and height for which these provisions are applicable, this method generally yields the lowest wind pressure of all the analytical methods specified in this standard. And For part 2, here is the part 1 explained, and in part 2 it says that this is an enclosed, specifically enclosed simple diaphragm low rise building. So now it is very specific. It's not a general one. It is very specific that it should be an enclosed simple diaphragm low rise building. Low rise means it should be less than 60 feet high. The height should be less than 60 feet. It says part 2 of chapter 21 is a simplified method to determine the wind pressure on the main wind frame resisting system of enclosed simple diaphragm low rise building that have a flat, gable or hip roof. The wind pressure are obtained directly from a table and are applied on horizontal and vertical projected surfaces of the building. This method is a simplification of the envelope procedure, as it is said. So this is a more simplified procedure and it is derived from part 1. Now, we are following this because our building qualifies all the requirements specified over here. The conditions are here. That is paragraph 28.5.2, the conditions. What are the conditions? For the design of main wind frame resisting system, the building shall comply with all of the following conditions. And there are 8 conditions which are here, and let's see what we did. Here I checked one by one that to qualify for this simplified procedure, the building is a simple diaphragm building as defined in section 26.2. Yes, it is. So I said okay. The building is a low-rise building as defined in section 26.2. Yes, that is also correct. The building is enclosed as defined in section 26.2 and conform to wind-borne debris provision of section 26.12.3. Answer is okay. Yes. The building is a regular shaped building as defined in section 26.2. Yes. The building is not classified as a flexible building as defined in 26.2. Yes. It is not a flexible. It is said that treat this as a rigid building. The building does not have response characteristic that make it subject to a crosswind loading, vortex shedding, instability caused by galloping or flutter. It does not have a site location for which channeling effects or buffeting in the wake of upward obstruction warrant special consideration. So this is also true. It meets all these requirements. The building has an approximately symmetrical cross section. That is also true. The roof angle is less than 45 degree. That is also true. It's a flat roof. The building is exempted from torsional load. Yes, that is also true. So that means this building, which is in our example, and we are going to calculate the wind load as per simplified condition or simplified procedure, it qualifies for this simplified procedure. Now let's go and check how do we calculate all. Now wind velocity is given as 144 mile per hour. Seismic category is 2. Importance factor is 1. Exposure is C. Now the wind force calculation in north-south direction normal to 60 feet. Let us assume that we are going to calculate the wind force which is normal to 60 feet side. And that means suppose the wind is blowing in positive y direction. This is for SAP convention. Now I am going to use a STAD just for demonstration purposes. So that should be in positive Z condition. So let me change. Now pressure on the wall, chapter 30, part 2. This is for component cladding. I'll come back to this portion. Let us go to main wind resisting frame system, which is calculated as per figure 27.3.1, which is reproduced over here. First step is, of course, determine the risk category of the building, which we have already defined. Determine the basic wind velocity V, which we have already checked. The parameters like exposure category, we know that is C. We have already defined KZT, etc. all. And here, that's a very important thing. Enter figure to determine wind pressure for H is equals to 30. So this is figure 28.5-1, and enter figure to determine the adjustment of building height for condition lambda, etc. So I'll go back to the standard. I'll show how it is done. So for wall pressure, the CMU wall, it has a height of 15 feet, and it's this height is the span. This is in the vertical direction. So the effective wind area is calculated as per the condition or as per the definition in 26.2, that is effective wind area A. The effective area used to determine the external pressure coefficient GCP, because this is all built in is there. So what we can do, that this is the figure which we apply. So we can come directly to the effective wind area calculation. That is equals to H multiplied by H by 3. H is 15, so this comes out to be 75 feet. So these zones, for these zones, A is defined as A should be minimum of 0.1 L or 0.4 H. So A comes out to be 3 feet, so 2A will be 6 feet. So that means here this section zone A will be 6 feet wide, and remaining 54 feet will be zone C. And you notice, if the wind is blowing in this direction, so only windward wall is loaded, no leeward loading is there, because this is the simplified procedure. Sorry. This is the simplified procedure, and the loadings are lumped here. So only windward wall will be loaded here, and the roof will be loading as per the procedure. If the wind is blowing in another direction, then only windward wall of this side will be loaded, and the leeward wall is not loaded over here. Now, if we see this figure 28.5.1, this is a simplified design wind pressure PS30 in PSF for exposure B at height is equals to 30 feet. Let me show you the figure 28.5-1. Here is this figure 28.5-1. In this figure, it says this is the simplified wind pressure PS30 in PSF for exposure B at H is equals to 30 feet and H is equals or 9.1 meter. So here the wind speed starts from 85 miles per hour, then goes down, and for us, since our wind speed is 144, so what I took this portion. And for the simplicity, what I did, instead of 144, I took it 145, so that the value will be a mean value or an average value for all these conditions. The first column is A, second is B, C, D, etc. So what I have done here. Same thing, I took copy over from there. The wind speed, if it is 140 mile per hour, then in zone A. Zone B is not applicable for us here because zone B is above the eave height. For us, this wall is straight, so only zone A is applicable. Zone C is applicable, D, E, and F, etc. These are applicable. And there are no overhangs, so we are not interested in EOH or GOH. So I took average of these two. For example, for A, I took 31.1 and 35.7, average it out, and then this is the way I calculated. So I calculated by taking average of this one, but this is net wind pressure, and this net wind pressure is coming from another equation which I'll show you now. The design wind load here, this para 28.5.3 design wind load, this design wind load should be calculated from this equation. That PS should be equal to lambda times KZT into P30, where lambda is adjustment factor for building height and exposure from figure 28.5-1. Here is the figure 28.5-1. This is the value of lambda. Our condition is exposure C, and roof mean height is 15. So that means for us the value of lambda is 1.21. And the value of KZT we have already defined. This is 1, and PS30 we calculated from that figure. Now at this point I want to emphasize one thing. If you see this equation in our old standard, that means ASC 705 or 702, this equation is something like PS is equals to lambda times I into PS30. So instead of KZ, the parameter I was introduced before. And now in this equation, the parameter I is replaced by KZ. Why? That's a good question. Because I now, for all the building types, the building categories is 1. So there is no use to still use a factor I which is under all conditions has a value of 1. And logically KZT is the topographic factor. So if there is a change in topography or it has a different value, then this pressure should be multiplied. This is a logical change in this standard. So what I can say that this is a realistic and logical change from ASC 705 to ASC 710 and onward ASC 716. So based on that, what I did, I calculated for load case 1 all these conditions. You can see I calculated for zone A, zone C, zone D, but I did not calculate for zone B because zone B is not applicable for our case. But for zone E, zone F, zone G and zone H, all values are calculated, and this is for wind speed 145. So now instead of 144 I am using 145. So just a simple, just for the sake of simplicity. And I'm just considering for load case 1 where the wind is blowing perpendicular to the longer face, that means the 60 feet face. Now what I did, I applied all these loads in stack. Now here I model like this side is our 60 feet, this is 30 feet, and this height is 15 feet. So I used quad element to model the walls only. Because I am not going to analyze this building, I am just going to show you how I applied the loads. So it's pretty simple. Now I'll show you the loads which I have already applied. Now for example this load case. As you can see blue, this is the area where it is 2A, and the value calculated was 40.411. Second is this area which is zone C, and all this load is applied over here. On the leeward side nothing, you can see no force is applied on the leeward side, right? And for the roof, this is E, F, G and H. So all these loads which were calculated before I applied on this model. And for the wall, let me go back to the wall calculation. For the side wall, I use the provisions for component and cladding, and here for component and cladding I use this side wall loads. And here the table is taken from figure 30.4-1. So let me show you chapter 30. As you know, chapter 30 is specifically used to calculate the wind load on components and cladding. Now here is the part 2, low-rise building. This is the simplified procedure. In this simplified procedure, the part 2 of chapter 30 is a simplified method to determine wind pressure on component cladding of enclosed low-rise building that have flat, gable or hip roof shapes. The provision of part 2 are based on envelope procedure of part 1 with wind pressure determined from a table and adjusted as appropriate. So again you can see the net pressure is calculated with a similar formula where no more I is used, rather case that T is used. The conditions are there. We have already checked that these are satisfied. And then P net 30, it can be calculated from figure 30.4-1. So let us see figure 30.4-1. This is figure 33. Figure 30.3-3. We are looking for 30.4. So here is the figure 30.4-1, component and cladding part 2, where H is less than 60 feet. Design wind pressure for enclosed building. This is for wall and roofs. So I took this first example because this is the closest one and all the dimensions are given. That means zone 5 is 0.6 times H, both sides. This is H, We know that our case H is 50, and similarly the zones at the roof is defined. So the same procedure I used over there, and I calculated the net wind pressure for all these areas. And at the end, with all these lambda etc., I calculated the final wind pressure, that is the net positive pressure for zone 4 and zone 5. So in this way I applied the loads on the side walls, zone 4 and zone 5, and both the sides are loaded with these pressures. So basically I use this area as calculated over here to load the side wall, and that you can see over here. So I applied the load on the side wall, which is acting from inside to outside, and on the other side also. So this is the simplest way of applying wind load for a very simple building, which is a low-rise building. So hopefully it will help you to calculate the wind load for low-rise buildings. And I can conclude now. Thank you very much. Please do not forget to subscribe my channel. Thanks a lot. Bye.